Okay. So I'll start with OSPF then. Let me just share my screen. Um, okay. So is my screen visible?
Yeah.
Yes.
Yeah. So OSPF stands for Open Shortest Path First. So as you guys might know it, so it is an open standard protocol. So unlike AIGRP, which was only made open source couple of years back, OSPF had been open source right from get go, and yeah, it is based on link state technology. So there is a difference between link state and distance vector. There's a lot of difference. So distance vector, you know, filters decides the routes based on the distance. Distance as in the number of hops, everything that has got to do with the distance between the routers. But link states, link state protocols have, decides the routes based on the state of the links. So whether the link states are up or down, or whether the speed between the links, or things like that. It looks at the variety of different parameters to decide the shortest path, not just the distance. Yeah. So why OSPF over RIP? So RIP has a limit. So that is the hard difference between OSPF and RIP. So as the network grows, you can't use RIP anymore. So OSPF, there is no limitation as such, but then so once the network grows to more than 200 devices, it is recommended that you split the OSPF into multiple areas. And RIP cannot handle VLSM until RIP v3. So RIP v3 can technically handle VLSM, but not in a proper sense that the modern IGP networks do. So OSPF uses IP multicast and also RIP converges slower than OSPF. That is obvious because all distance vector protocols converge a little bit slower, and OSPF also has load balancing and authentication. And yeah, RIP doesn't have any areas; those are flat networks. Uh, so in fact, there are no concept of areas for any other routing protocol except for OSPF. So yeah. So what do we mean by link states? So yeah, as it is written, so you could think of a link as being an interface to a router. So the state and description of the link, or the state and description of that interface, and the relationship to that uh, of that interface to the neighboring routers. So that is the link state. So that is what is the important point when it comes to link state protocols. So a description of that would be the IP addresses of the interface, the mask, the type of network that it is connected to, the routers that are connected to. So all these collections together form the link state database, which would eventually get propagated throughout the network. So LSDs. So link state databases are also one of the things that are advertised on OSPF. So what is SPF? So if there is any change, so LSAs are propagated throughout the network, and uh, with respect to link state algorithms, the entire topology knows the entire. I mean, the entire the all routers in the topology know about the entire topology. So what do I mean by this is, so in RIP, any particular router will only know about its neighboring routers. It will not know the entire topology. But in case of OSPF and other link state protocols, all routers will know the entire topology. So which means that if there is any node that goes down, or if there is any change in the topology, that needs to be propagated all along the network. So this is one thing. So since the information should be propagated all along the network, so obviously there will be flooding. So all exchange link states are exchanged by means of flooding. So every router that receives a copy of link state update should forward it to the other routers as well. So after all the database exchange is completed, it will go to the full state. So I'll explain the different states in OSPF later. So uh, yeah, so as you know, it calculates the shortest path using Dijkstra's algorithm. So this is cost calculation, which is not really required right now. So areas and border routers. So as we split the OSPF into multiple areas, so every area would have a area border router with the backbone area. Backbone area as in the area 0. Of course, there are ways to bypass things like that. You can have a virtual link, but let's look at that later. But as of now, all areas must be directly connected to backbone area or area 0. So the routers on the interface of every area with area 0 are called area border routers. So area border routers would know the entire topology of its own area and the route to area 0. But other routers except for area border router in those areas would not know the information about the other area. So it's basically summarized. So one area would not know the information about the other area. So in that way, the routing table would be minimized. So the processing power will also be minimized. So that's the whole point. Link state packets. So there are different types of links. Let's go through them. Yeah, LSA 3. So there are like 11 types of LSAs. Let's look at LSA 1. LSA 1 and LSA 2 would give intra-area routes. So which means that these link state advertisement packets would give the routes within the same area. LSA 3 packets would give inter-area routes and they will originate from the area border router because area border router are the ones that would give the inter-area routes. LSA 4 would give inter-protocol routes. So for example, if there is another router that runs RIP, for example. So there is a legacy router that runs RIP. I'll show you that micronugget video that me and Pearl had watched earlier later in the presentation. But for now, let's visualize this. So there is a router that so there are like 10 routers that run OSPF and 2 routers that run RIP, and these two should be merged. So the RIP routes should be redistributed to OSPF and vice versa. So for that, LSA 4 packets are used. So LSA 4 packets are used to communicate between different protocols like RIP or EIGRP, etc. So LSA 8, okay, LSA okay, 4 and okay, 4 is there, 5 is not supported, 6 is not there, 5 is uh, 5 gives inter. Okay, LSA 5 gives inter autonomous system routes. So inter AS system. So for example, there are multiple OSPF. So for example, OSPF AS1, AS2, AS3, for example, for different departments or for different companies, etc. So in that case, if one is redistributed onto another, so for that LSA 5 packets are used. And 8 is used for BGP OSPF interworking. 9, 10, 11 are opaque SLAs for specific MPLS internetworking. So let's watch this one out. Okay, let me do the one thing. I'll
It's on YouTube version. You can search there.
yeah. I am searching. I've just passed the screen share. Okay, let me just have it audio. Okay, so is it visible?
What is MPLS?
Yeah.
Is it audible also?
Yeah,
Yeah.
it's audible.
Well, it's an acronym. That's short for My Pulse, as in my pulse is going up talking about it because it's an amazing technology that makes it a cool time to be alive. Okay, that was really cheesy, but here's what MPLS is. Multi-protocol label switching is a way of connecting your sites.
Hello? You're going to explain OSPF or MPLS? Hello?
Oh, yeah. Just a moment.
You by mistake you open MPLS video.
Yeah. Thanks for reminding.
The ever confusing OSPF area and LSA types. I remember this being a really confusing topic for me when I first learned OSPF, so I hope this micronugget can help you out. First off, the areas. When you first begin with OSPF configuration, you are required to create area 0. Some businesses never grow beyond that. That is known as the backbone area. As the business begins to grow and you keep adding more routers, your routing table eventually gets a little unruly. Like there's too many routes in there, there's too many changes, networks going up and down, processor cycles being wasted, and that's why we break into multiple areas to begin with. In link state protocol, which OSPF is one, the rule is that all routers in the area have to have the same link state database. They have to know about everything. So the only way to hide some routes or to do summarization, a big routing efficiency mechanism, is to break into multiple areas. That's where the standard areas come in. Standard areas is just, hey, I want to make things more efficient. I want to put some routers over here and do summarization between these two areas. So maybe all the 10.1 networks are over here, all the 10.2 networks are over here. You get the point. So stub area is where you have a area that is limited in the information it can receive. So you can see this cloud up here. What's in there? Maybe RIP routes, maybe EIGRP routes, maybe BGP routes. Who knows? It's another network. You may decide to redistribute or send those routes into your system, and at that point, they are considered external routes. A stub area says, you know what? I don't want that in my routing table because, you know what? I only have one real exit point out of this. It's a fairly small area, so why flood these guys with all that information when really they're all just going to go this way anyway? That's what a stub does. A stub says any external route is blocked here and replaced with a default route. So all of the routers in that stub area automatically get a default. Now Cisco stepped it up a notch and said, we're going to create a totally stubby area because their logic was, well, good grief, if you're filtering these routes because you only really have one exit point anywhere or a couple exit points, smaller system, why not go all the way and lop it all off? So a totally stubby area says, I'm going to filter the external routes and the routes from these other systems and replace it all with a default route, which makes the routing table inside of that area really efficient. That leaves a not so stubby area, which is one of the coolest name technologies I've ever heard. A not so stubby area, or some people call it an NSSA, is an I grew unexpectedly sort of design. Let's say Area 1 represents China. And in China, they brought up a partner relationship with another company that is running RIP. And you want to start sending those routes into your system. Oh man, now we're breaking the rules of the stub. We want to keep our stub factor going on because we want efficient routing tables. But the whole idea of a stub is that it will filter external routes. Well, you just brought more external routes in the system. So they say, well, let's bend the rules. That's a not so stubby area. So what it does is kind of camouflage those routes. I'll explain that in a second. As it comes into the system. And once they're through the sub area, they appear as external routes. Understanding those area types helps understanding the LSAs so much easier. First off, LSA, what's that? Link state advertisement. It's a router's way of communicating information in OSPF. So for example, router 1's plugged into some networks. It wants to tell people about it. It's going to generate a type 1 LSA because it's a normal router. It's going to say, hey, everybody, I'm router 1. I'm plugged into these networks. Add them to your link state database. Type 2 LSA is for the designated router. See, when you take a bunch of routers, plug them all into one switch, you don't want them all forming neighbor relationships fully anyway, because it becomes a big mess of updates anytime something happens. So they elect one router to be the designated router, and the type 2 LSA just lets everybody know who that designated router is. Type 3 LSA is a summary LSA. That happens anytime a route goes between areas. It doesn't even have to be summarized. Isn't that kind of weird? So for instance, router 1's plugged into the 10.1 network, 10.1.1.0/24. As it moves from area 2 into area 0, it converts from a type 1 LSA to a type 3 LSA because now everybody knows it's summarized, even though technically it may not be summarized. Type 4 LSA is the location of an ASBR. What's an ASBR? Autonomous System Boundary Router. Routers that allow you to leave your system. So so the routers can all find the best way there. By the way, I forgot about this. Area border router. These are the routers that are able to summarize between the areas. Finally, type 5 LSA is the external LSA. This is the routes that are coming in from outside the system. So type 4 is where's the ASBR? Type 5 is here are the routes from the ASBR. Now, combine these together. Stub area does not allow type 5 LSAs. Totally stubby area blocks completely type 3, type 4, and type 5 LSAs. Doesn't care about them. That's how it shrinks the routing table. Not so stubby area, that uses an LSA type that's not even in this list. Remember I said it kind of does a secret ninja thing and tunnels routes through the area? It uses a type 7 LSA. And all that is, think of it like one of those masks that people use in the play, you know, the big smiling Shakespeare mask. They put Shakespeare masks in front of all these type 5 LSAs coming in, and they're like, no, these aren't type 5 because otherwise the stub area will block them. But once they make it through that system, it rips off that type 7 mask and really says, they're really type 5s. That was the fastest I've ever described.
Okay, so I don't know how much of that you guys got. So let me just explain it briefly. So backbone area. Backbone area is basically area 0. Standard area is all other areas. So stub area. So what do they mean by stub area? So non-OSPF protocol routes. So if there is REP or AGRP that has, that is not OSPF or that is external routes. So those kind of routes are not necessary within areas that are not directly connected to it. So for example, area 0 is directly connected to a RIP route, but area 1 has only one path to area 0 or maybe two paths. It is not directly connected to the RIP system. So why would area 1 need the routes of those RIP system? So stub area blocks those kind of external routes. So totally stub area goes a step further and says area 1 does not need the routing information of the routers within area 2 as well. So even the routes within area 2 will not get propagated to area 1. So it will just compartmentalize the entire network. So not so stubby area gives a little bit of exception, because if the network grows on one end and not on the other end, so now you can't really change area 0, because once you define area 0, it is very difficult to change it. So in that case, if there is some other company that is attached to R5, like he said, so if that company runs a different protocol, so in that case we need to make an exception. So not so stubby areas makes an exception for that particular system. So LSA type 1 is used, as I said, is used for within intra area advertisements, and LSA type 2 is for network LSAs, which is like for T1 it will just give the network addresses, and LSA type 3 gives the summary LSA, which means that the area border router summarizes the entire route for that area and then propagates it to area 0 or another area. So in that case, LSA type 3 would go as a, LSA type 2 would go as a type 3 to area 0, if you got my point. Okay, so LSA type 4 is a summary LSA for the ASBR. So from the ASBR, the summary routes would come as LSA type 4 LSA, type 4 LSAs. So type 5 LSAs are external. So once it enters the area 0, it will become an external route. So these are different types of routes that are getting advertised within OSPF. Okay, so moving on. Okay. Okay, these are authentication. There are two types of authentication: simple password and digest authentication. So these are not exactly important. So there's just this command IPOSPF authentication key my password. So you can give that to authenticate it. So if you want better security, you can also do message digest, which uses encryption, so that people who snoop on your wires don't get the password. So so OSPF has special restrictions when multiple areas are involved. So this is obvious. As I said, backbone areas are area 0. So every area should be connected to area 0. When designing network, it's a good practice to start with area 0 and expand to. It's obviously impossible to start with any other area. So unless there is area 0, OSPF wouldn't work properly. Backbone has to be the center of all areas. Okay. Virtual links. So if you guys remember, I would have told earlier that there is a way to bypass this restriction. So virtual links are used for two purposes: linking an area that does not have a physical connection to the backbone. So in the future, for example, if your network expands in such a way that it is impossible to have a direct connection to area 0, virtual links are kind of like a band-aid solution temporarily. So if you have too many virtual links, it becomes very difficult to troubleshoot and have any errors resolved. So for the time being, to have the network up and running, you can have virtual links as a temporary solution, patching the backbone in case discontinuity of area 0 occurs. Yeah, DR elections. So DR elections are done via Hello protocol. So these are not so these are asynchronous. So if one DR, if DR goes down and BDR becomes the DR, so as soon as DR comes up, the roles would not get reversed. So BDR would remain the DR, and the past DR would now become the BDR, something like that. So it is not synchronous. That's what I'm saying. So the router with the highest OSPF priority. So priority. So there's something known as like router ID. So you can router ID is based on priority. So if you don't give any priority, in that case the highest loopback IP address would be the router ID. And if you don't have any loopback ID assigned, so the highest IP address of the assigned interface would be the router ID. So the highest router ID would become the DR. So in case of the tie, the router with the highest RID would win. So that is the same thing. Yeah. So now coming to an interesting part. So building the adjacency. So there are like 7 states. So these are the states that you generally would troubleshoot. So down state. So no information has been received from anybody in the segment. So when there is no information, no hello packets, nothing. So the OSPF is said to be down. Attempt. So attempt is not really important in this context because it is only that is only there in frame relay routers and not really there in our modern routers. Okay, so the second state is init. So when the interface has detected an hello packet coming from the neighbor, so it has not established a bidirectional communication yet, but the one of the routers in one of the interface has received some hello packet of OSPF. So that is the init state. So two-way. So there is a bidirectional communication. So it has received hello, and the router that received the hello has also sent an acknowledgement. So now there is a two-way communication. So yeah, at the end of two-way stage, routers will decide whether to proceed in building an adjacency or not. So this decision would be based on whether one of the routers is DR or BDR. So depending on whether one of these routers are DR or BDR, the link would be established, and that link would be updated on the routing table. Xstart. So after this, I'll also say what are the common errors that will occur in all of these stages and how to troubleshoot them. For now, let's just understand the stages. Xstart. So routers are trying to establish initial sequence numbers. Okay. So yeah, so DVD packets are sent by the higher router ID. So that is for the Xstart state. And so DBD is database description packets. So those database packets are sent during Xstart state, and in the exchange state, they're actually exchanged. So they will describe their entire link state database. So for example, the router would say that these are the routers that are connected to me and via these interfaces. And similarly, the other router would also exchange its own information. In the loading stage, verification would happen. So what do you mean by verification? So after all the information has been gathered, so it will verify that whether this is correct or whether this is correct. So at the end of exchange, not all routers would have all information. Almost all routers would have almost all information. So the remaining bits and pieces are merged in the loading stage. And the full stage, in this case, the adjacency is complete. So the neighboring routers are fully adjacent, would have similar, they would all agree on the same database, same topology. So this is what the topology looks like. So all routers would agree on that. So now let's go to the troubleshooting part. Okay, so is it visible, or maybe you guys can zoom? Yeah. So there are like different types of errors, and for this, what would the customer do and what should we do? So there are like flowcharts given for each of this. So let's look at the different flaps and different errors for this. So if the state is init, so you perform an init state check. So this would generally not happen, but then if it happens, you can perform a state check. And generally, the OSPF errors would get stuck on Xstart or Exchange. So this would happen because of MTU mismatch or layer 2 mismatches. So what do you mean by layer 2 mismatches? There's a lot of things: hello timer mismatches, MTU mismatches, bandwidth mismatches, and different types of wrong types of cabling used or something like that. Okay, so all layer 2 errors would those would be the reason for uh, Xstate or Exchange, the OSPF getting stuck on those states. So when the state is loading, and if the OSPF gets stuck on that, so there could be a corrupted packet check. So you could there could be any CRC errors or any corrupted packets traveling through the OSPF, something like that. So that could be one of the reasons. So if there is a error on two-way state, so maybe one of the routers is able to communicate, the other one is not able to communicate. That might be due to any ACLs or something like that. Okay. So if there is no command output when OSPF is flapping, you could check the link state itself. So there are like various for every flaps there are like what to do, full adjacency check, like what else should be done for this. So yeah, NBMA are completely different kind of devices that we are not going to explore for now. So for MTU layer 2 check, so to determine whether there is a layer 2 problem, you must check whether the MTU is same for both the, so MTU is basically maximum transmissible unit. So those must be same for every layer 2 device directly connected to each other. So you could use show IP interface command to find that out. So yeah, and after doing that, you can also check whether the OSPF has come up. So corrupted packets check. So for this, so OSPF 4 PAD LSA type should be if there is some kind of error message like that, so that means that there is a corrupted packet. So so we must perform a CRC check and find out that packet and find out the cause of the problem. And this is two-way check. So for two-way check, you can give a show IP OSPF interface so that to check whether the interfaces are up on both sides. Yeah, so by that, if one of the interface is down, you have eliminated the problem. So link check. So you can give show IP interface command to check whether the link is up. These are like basic commands. So if link is not up, nothing would work. Not even not OSPF, not anything. So you can also check for that. So full adjacency check. So you can also if there is no adjacency established, you can give show IP OSPF neighbor to check whether the neighborship is established. And if there is no neighborship, you can find out the reason whether the IP addresses are getting propagated properly, or whether the network address are correct, subnet masks, wildcard masks are correct or not. So you can check all that. So external LSAs, the problem could also be the part of external LSA. So if there is some other routing protocol that is connected to this OSPF and redistribution is not done properly, that might also be a problem of routes not getting propagated properly. So you can give show IP route, show IP OSPF database external. So to filter out the routes that are problematic. So NBMA is not there. So ACL check. So ACLs could also be a problem, like I said. So you could try disabling ACL and then re-enabling it again to check whether that is the problem. And so OSPF has a port number. Just check. Yeah, 89. So you can check whether the ACL is blocking that particular port. So you must enable that port for OSPF work. Okay. So after all that, you can ping. So whether if the ping is working and OSPF is not working, so you can eliminate that. The connection is there. The neighborship. I mean, there's no problem with layer 2. You can eliminate stuff like that. So this is the same thing. Frame relay. So uh, so frame relay environment is not there for us. Okay. So area type check. Okay. So if the neighbors are connected with different areas and the advertisement is not properly propagated to different areas, in that case, if you meant to configure two routers in the same area and you by mistake configured it in separate areas, so that could also be a reason. So you could use show IP OSPF interface to check whether the routers are there in the same area. So not just that, so the interfaces that are connected to each other should also be in the same area. So no matter whether you're using multiple areas or not, so both the interfaces of any router should always be in the same area. So the area splits the router, not the interface. So if you visualize the area border crosses the router. So different interfaces on a router can be in different areas, but never the links themselves. Okay, so even if you use multiple areas, two different interfaces of a same link should always be in the same area. So you can use show IP OSPF to check that. So hello and dead intervals. So if you are manually changing any one of those, generally they would be the same. But if you change it, make sure that you change it for both interfaces. Yeah, thank you. And let me open BGP next. Are there any doubts for this?
No.
Okay, so okay, so BGP, why BGP? So it's scalable. We have OSPF, we have VHRP, we have everything, but then BGP is required for large networks. So uh, it's super fast, it converges super quickly, and it's reliable. So once you configure BGP, it will go on forever without needing any external intervention. So that's why BGP are predominantly used in ISPs and large networks. So yeah, recursive routing failures. So let me explain how this works. Um, okay. So what do you mean by recursive routing failure? So for example, there is a tunnel. I will give you an example like using a tunnel. So for a tunnel to work, there must be a static route, but you are defining a static route based on the tunnel. So it's like two unknowns depending on each other. So you need something for something else to work, but for that something else, you're again referring to that something. So it's kind of a loop. So in BGP, how that works is, so if you're configuring some other protocol, say uh, OSPF, so obviously for BGP to work, there should be another IGP protocol enabled. So I think you guys know that. So let's say that IGP protocol is OSPF, and in OSPF, you are redistributing BGP again, and you're using that to define a link, and you are defining that link itself in BGP, showing OSPF as the source. So it's like two protocols showing each other that they know the route, but nobody knows the route. So that's something like that. So if you give a ping, ping won't work, and if you give a debug command, it will be a continuous loop. So that might be a reason of flapping in BGP learned routes in routing table. So if you observe this output piece, so there are like there is 172.16.1.0 and 20.20.20.0. So there are two networks learned via BGP. So uh, if you notice carefully, so 172.16.1.0 is also learned via 2020-2020. So and 2020 is also learned via 2020. So there is a loop there. So if this happens within a minute, it will go down. as you see, so now the BGP that 172 is not there because it is a recursive loop, and now it goes down because eventually BGP realizes that it doesn't really know that route, and after that it will again repropagate the same route, and it will again assume that it knows the route, and again it will check that it really doesn't know the route, and then it will drop it. So this happens like repeatedly. So this is the recursive, routing problems. Yeah, so the connectivity fails, and in order to observe this, when the routing table of router A has a BGP learned route in its routing table, a ping to the valid host fails. So even though the show IP route command gives the route to that entry, the ping fails. So recursive routing problem could be one of the problem that is causing this. So yeah, observe the route to the BGP peer 2020-2020. The route flaps between the two next stops consistently over every minute or so. So uh, yeah, the route towards the BGP peer IP address is learned through BGP itself. So generally, the route towards the BGP peer should be learned via some other protocol like OSPF, but in this case, it is learned via BGP itself. So the same protocol is looping over itself. So after approximately a minute, it will change to this. So it will change to known via static, and then the BGP will again say that it knows this, but in fact it doesn't know that. So it goes on. So whatever I've explained this, they have just given this in a paragraph. Okay, and if you give debug IP routing 1, okay, 1 is basically an access list. So if you just give debug IP routing, there will be a lot of debug outputs. So to filter only whatever we require, we just give the IP addresses 2020-2020 and 172.16.1.0. So these are the two IP addresses that that are of importance for us now. So we'll just create an access list and debug IP routing 1. So that access list would be applied, and only the matching debugs would be displayed. So there would be this error known as probable routing loop. So this means that there is a recursive routing loop in our you know, routing protocol. So yeah, so there's that. So for this solution, okay. So for this, you need to create a route that is apart from BGP. So you need to create a static route. You need to create a RIP route, or you need to basically create another routing protocol that actually knows the route instead of looping onto BGP itself. So for eBGP peers, you need to have a IGP protocol running within it. So BGP is basically a layer. So within the layer, the actual routing would be done by IGP protocols inside it. So without IGP, BGP wouldn't work. So that IGP should be there, and BGP shouldn't loop in on itself. So that's basically it. Route dampening. So route dampening is a feature of BGP that is used to minimize the propagation of flapping routes. So if in case there is any flapping, route dampening will identify it and it will shut down that interface. So instead of wasting the processing power on constantly turning on the interface and turning off the interface, uh, BGP dampening would shut down the interface so that at least the administrator would know that there is something faulty happening there. Yeah, there is some parameters like half time, reuse, suppress, and max suppress time, that you could configure so that within that interval, it will recognize the flapping. Okay, so yeah, so BGP is also done. Any doubts here? I meant to close it, but it stopped sharing. Okay, let's look at Ether channel load balancing. Uh, as you guys already know from your CCNA, Ether channel is used to club multiple physical interfaces into a logical interface. This is used in switches. So if you have like a lot of traffic that you cannot, transfer within one Ethernet cable, or if you want to have a larger speed, Ether channels can be used. So there are two Ether channel aggregation protocols, LACP and PAGP. So what is PAGP? So PAGP is Cisco proprietary, and it automatically creates Ether channel links. So PAGP packets are sent between Ether channel capable ports in order to negotiate the formation of the channel. So PAGP does not form a bundle on ports that are configured for dynamic VLANs. So there are some restrictions on this. So PAGP requires that all the interfaces, all the ports be in the same VLAN or are configured as trunk ports. So when a bundle already exists and VLAN of a port is modified, all ports are modified to match that VLAN. So this is one thing. So if you already have whenever you have a Ether channel and you modify something else that is related to this on the particular link, the entire thing goes down. You might have watched this during those lab assessments. So whenever you configure Ether channels and you after configuring it, you modify something on the separate links, the entire thing would go down. And if you configure PAGP and then you configure one of them into a VLAN, the entire thing would automatically get converted to that VLAN. So that is that is done by PAGP. So obviously PAGP does not group ports that operate at different speeds or port duplex. So everything must be the same. The MTU bandwidth again, duplex parameters and speed parameters. So if the speed and duplex change, so the PHP changes the port speed and duplex for all ports in the bundle. So there are four modes of auto, desirable and on. So if there is an auto mode, so unless the other side is on or desirable mode, it will remain off. So if it is desirable, it will force the auto modes to become on. So yeah, this is the difference. So only the combination auto desirable and desirable and on allow the formation of the channel. Okay, so the device is on the other side. So the device on the other side should also enable PAGP to have this working. So what is LACP? LACP is a protocol defined on IEEE standards, so it is open source. So it also does the same thing typically, and so how do they differ? So LACP is passive. So this only the naming differs. So in LACP, the auto mode is called as passive, and in PAGP it is known as auto. But otherwise, what they do in the end is the same thing. Yeah. However, PAGP is also on demand where Cisco equipment is embedded in your network. Yeah. So PAGP only works with Cisco devices, obviously. Yeah. Thanks, guys. I guess that would be it. You can ask doubts or maybe you can proceed with your presentations.
Can I go next?
Yeah, sure.
And Arjun, you know what? I saw it just now. You wrote packet forwarding in my name. I'm really sorry. Yesterday when I saw it, I thought, okay, there's only one topic in my name. But today when I saw it, just now I saw
Yeah.
it.
That's okay. No. That's okay. That's okay. That's okay. That was just Parul suggested it, and I just put it. There's no need for doing that.
Okay, so my topic is high secure memory troubleshooting. So these are the topic when for like troubleshooting when there is a lot of memory used or we have memory CPU utilization is not up to the mark. So the first command we have is, am I audible?
Yes, you are audible.
Okay, I thought I was on mute. Yeah, so the first command is we have show version command. We all have seen this command yesterday also. So these are the fields which it shows, and these are the descriptions. So first the field is version. Actually, I am not able to access that auto part. I'll show it in the examples only. Yeah. Yeah. So as we all know, this is the version. Yeah, this is the version, and Yeah, it also tells about the ROM, which is the bootstrap version string, and the router time up. Router. It also tells us about the router time up, the amount of time the system has been up and running, and so the router time up is here. This one. This is the router. This is the router time up. It has been up. Its uptime is 6 days, 21 hours, and 49 minutes, and it also tells us about the system restarted at this time. And also it tells about the image file which is already stored in it, and at last it tells us about the configuration register. Yeah, and else Cisco, this one, it's about remaining output in each source hardware configurations. The remaining output, it shows the hardware configuration. The next command we have is show process memory. It shows information about the active processes we have, and this is the output. Arjun.
Arjun, can you put yourself on mute?
Yeah, this is the output of show memory processes. I just ran it in the 907. Arjun.
I muted him. I muted him.
I'm muted.
Okay, this is the command show process memory. This is the output for that command, and at last it also shows the total of the total holding processes. This is the total, and we all know, like allocated must be the allocated memory, read memory, and the holding memory, and get buffs is the number of times the process has requested packet buffer, and red buffs is the number of times the process has relinquished a packet buffer, and processes is all the process's name of, obviously, and the total is the total amount of holding processes. Yeah, this is the command check memory usage on iOS XE. The command is show platform software status control processes brief. It is used to see the current system memory usage, and now it is showing it is healthy. And apart from healthy, it shows healthy, warning, or critical. It depends on the amount of memory, whether the memory is free or not, and about the CPU also. About the CPU utilization, I have written all the headings, what it means. CPU is the allocated processor. The CPU is the allocated processor, and user is the non-Linux kernel processor. System is the Linux kernel processes. Nice, it is the number. These are the low priority processes, and idle is the percentage of CPU which is inactive. IRQ is the interrupts, and SIRQ is the system interrupts, and IQ is the percentage of the CPU which is waiting for IQ. And yeah, now we have the next command, which is monitor platform software process RP active. This is used for it tells us about what is the memory usage for each process in iOS XE. So whenever we write this command, it might show something like this: terminal type network unsupported. It might prompt you to type a terminal name. So for that, we can type this terminal name, for example, terminal type VT100. So then we can run this command. And yeah, RES, it shows the non-stack physical memory processes, and SHR, it shows the shared memory processes, shared memory which is used by a process, and RES plus SHR, it is the total amount of process. Yeah, so this is the show platform hardware QFP active infrastructure XMEM statistics command. QFP is basically, it is a type of processor, quantum flow processor. We can say it, to get in some details, it is like it put all the services from layer 2 to layer 7 on a CPU itself. So QFP is basically a processor only, and I was not able to run it in 907 because I think it don't have a QFP processor, I think. So yeah, XMEM is, it contains IRAM, DRAM, SRAM, and BQS related memory. IRAM, DRAM, I think these are a type of RAMs, and it shows differently that the amount of memory used by IRAM and DRAM here. And then next we have show platform hardware QFP active infrastructure email statistic user. It tells us about the memory which is used by each user. So these are the username. These are the memory used by this user, and we can see the highest memory is used by SBC here. When we want to see that like how much memory is used by this user, so we can use this command. And the last command is show platform hardware QFP active TCAM resource manager usage. So TCAM is basically QFP. I told you QFP is a kind of processor only, and TCAM is ternary content addressable memory. It is a kind of memory in in layer 2 or layer 3 switches, and they can store the routing tables in TCAM. So yeah, and it tells us about the total TCAMs. It tells us about the total TCAM free cell entries 131072. These are the free TCAM cells. When we are very low of these free TCAM cells, the ESP might, I don't know what is ESP, but it was written somewhere that when we are very low of these free TCAM cells, so the ESP it may show some logs, or it might crash sometimes. Yeah, that's it from my side.
Okay, I'll go next. Start with MPLS. Yep. So am I audible and my screen is visible, right?
Yeah.
Yes.
Yeah.
Okay. So we'll just have an overview of MPLS. So MPLS is a multi-protocol label switching. So why we needed MPLS? So basically it combines the performance and capabilities of layer 2, which is the switching part, and it also provides the scalability for the layer 3. So the thing is, whether it belongs to layer 2 or it belongs to layer 3, it belongs to neither of them. It belongs in between. So sometimes we may call it as a layer 2.5. So it is between the layer 2 and layer 3, and it uses the set of protocols, which is the label distribution protocol or the RSPP for forwarding the packets. So instead of the IP addresses, it forwards packets based on the labels given. So these are the certain terminologies we'll be using. So labels, what are the labels? These are the 4-byte long identifiers to each packet. So MPLS will push the label, it will also pop the label. So all these things are done by the MPLS. The next is the label switched path. What is this? This is a path or the LSP sequence. So a path which a packet will follow will determine a label switch path. A tunnel which is established between end to end, or one or more LSP per tunnel. So in the diagram, mm, supposedly this. So, so if a packet will follow a certain path, so that path will define the LSPs which follow the R1 or R3. So all these for R4, R1, R3, and R6. So this will combine an LSP. So these R1 and R3 are the PE routers. This R4 and R6 are the CE routers. So so all these terminologies are mentioned here. And label switching routers are those routers which help in the switching. So LSS routers will be that PE routers. So and the middle router as well. And edge routers are there which are present in the different areas. Like the ones which are the corner are the edge routers also. So this is the typical format for an MPLS header. It will have a label byte, label value. The label value is, we define the label value using this MPLS label range 100 to 199, the last point you could see. So this is the label value. We could give any label value. So We could give 200 to 300. So these are the label value, and then MPLS will assign the label based on these values only. So this is the label value which holds to 20 bits. EXP is 3 bits. EXP is the exponential bits. These are used for the quality of service. We don't have to go in detail of that, but these 3 bits are used for the quality of service. This S bit is the end of stack. So whether we have reached the end of stack or not, so this bit will define that. And TTL is the time to live. So these are the following operations which MPLS could perform. So push is that when we have received the packet, so we have to push the label. So the ingress router, the PE router which is there at the starting, will push the label. The intermediate routers will swap the label. So their operation is to swap. Like after one hop, it will automatically swap the label. It will assign a new label. And the egress router, the one which is sending packet to the outside, will pop the label. So that is done by the PE router, which is there at the extreme end. So there is no label, the stack is removed, or the packet is forward is unlabeled. This action could be performed like no label is that untagged. Sometimes the label comes untagged. So in that case, all these operations would be performed by the LERs, and aggregate. In this, the label stack is removed and an IP lookup is done on IP packet. In this, the label will be removed and it will look for the IP packet when it will send it to the outside world when it needs the IP packet of that IP address of that packet. So that operation is known as aggregate operation. Few like from 0 to 15, there are reserved labels. So we cannot, our system will not assign a label like 2 because it is already reserved. So all these reserved labels, we cannot assign that. So for example, label 3 is used for explicit pop. Like whenever I receive a packet which has a label 3, so that router knows that it has to remove the label. So that's the reserved labels thing. So all those 0 to 15 are the reserved labels. Okay, so this is the IP packet data which is entering the MPLS cloud. So we could see it has the destination, MAC address, IP address, it has checksums, time to live, and all those values. Once it enters into the MPLS cloud, the first thing would be to push the label. So what our PE router will do, it will first of all push a label. So it will give a label 100, and all those other values like EXP is 0, S bit is on because it's the last label which has been pushed, and TTL is the time to live. So this is the first push operation that has been done. Now this router will pass it on to the next router and it will swap the label. So once it will, now the label becomes 200, earlier it was 100, and all those values remain the same and TTL gets reduced by 1. And after, yeah, so once the label get removed, what it will, that it will have, suppose at the last router, which is sending the packet to outside the MPLS cloud, it will remove all the labels. So all the MPLS factor has been removed. So outside the MPLS cloud, they are unaware about the labels. They don't know what label exists, what label were given or not given. So they are completely unaware. So all these MPLS, the last P router will remove all these labels and will start the routing process as it is. So it will look for the IP address and the destination IP address. So we'll be looking at the configuration for MPLS. So there are a few steps. The first step is that we'll be referring to this topology, the topology we referred in the Robert Perkin guide, and I put the link if you have to go through that. So we'll assign the IPs and loopbacks to all the router. Here I put for the one, but we'll assign the loopbacks for R1, R2, and R3. R1's loopback is 111, R2's is 222, and no, we won't assign it to R2 because we don't need it. So R1 and R2, R3 will be assigned their loopback addresses. Similarly, R4 and R6. Second is LDP on all interfaces in the MPLS core. So there are why do we need LDP? LDP is the label distribution protocol. So label distribution protocol is responsible for distributing the labels among the various packets. So it uses the UDP source port 646 and it will exchange the hello packets for the neighbor relationship. Once the neighborship is formed, they will form a TCP connection because they can't use UDP because they need a dedicated link for the further because they need an LSP. So for that they need a TCP connection. So they'll use a TCP connection once the neighborship has been formed, and before that they'll be using the UDP. And for TCP connection also they'll use the same port 646. And yeah, this was the command which I discussed earlier. For router 1, we could give 100 to 199. For router 2, we could give 200 to 299 and so on. So, and MPLS LDP autoconfig is the command to enable the MPLS in our system. And the third step would be we need a BGP between R1 and R3. Why do we need that? Because we will be forming an MPLS tunnel between the R1 and R3. There is no physical tunnel, but we need an MPLS tunnel between R1 and R3 because we don't know that outside the MPLS cloud, they don't know that R2 exists. So there should appear that R1 and R3 are directly contacting with each other. There's only one router, but suppose there are many routers. So that would be the same case. They should not know that all P routers exist. They should only know that R1 is directly connected to the other end's PE router. So that's why we need a tunnel. And for that, we'll use the commands as neighbors and no auto summary. And yeah, we'll be putting into the VPN4 and for the tunneling we need the VPN, so that's why we are putting it. And for the R3 router, will be considered neighbor as 1.1.1.1, and all the process will be the same. Now we'll need VRFs. So what are VRFs? VRFs are the virtual routing forwarding. So it will allow us to have a virtual like multiple tables. One is for the global and another one would be the VRF forwarding table. So they could multiple instances of a routing table could coexist in a router and they could work together. So they both will be independent. They don't know what's the value of one router and what's the value of another routing table, but they could coexist for a single router. For example, if R1 was in PE and it has two customers which has these IP addresses, they could accommodate in different VRFs so that it could distinguish between them too using the route distinguishers. And now the route distinguishers and route targets. The RD and RT, which we previously also discussed. So RD, what RD does is it makes the VPN addresses unique in the MPLS network so that it could distinguish around what, like which customer is sending me this packet. And the route target will depict that which data or which packet could be exported and which packets could I import on the PE router. So that would be dependent on RTs. So these are the commands we would use for that. And once we are done with the VRFs and we have created the VRF table, here our VRF table name is red. We could give any other name. So once that's created, we would move on to our last steps so that now we have to redistribute OSPF into BGP and we have to redistribute BGP to OSPF. So that would be done because they don't know about it. Okay, MPLS Cloud has a OSPF or MPLS Cloud has BGP and the outside has OSPF. So to do that, we need the redistribution. So that could be done using these steps. And along with that, we could also keep on checking about the various verification commands like MPLS interface, or when we have to know that LDP leadership has been formed or not. We need to know the VPNs, like the tunneling summary. Then we could use that command. We have to know that what IP routers VRF will choose. Then we can use these two commands for that. Yeah, that's it for the multi MPLS. Yeah, just this is a short topic. So BFD, why is BFD is needed? We know that OSPF takes a lot of time in convergence, and to reduce the time of convergence, we'll be using the bidirectional forwarding detection. So yeah, it is a detection protocol. It is used for fast forwarding path failure detection, and for the routing protocols, we have implemented using the OSPF. It also provides a consistent failure detection method, and since the forwarding path failures is done at the uniform rate, it is more reliable, it is easier, and the reconvergence time is much more consistent and predictable. Okay, so we'll see the functioning over here. Yeah. So firstly, what happens is when OSPF discovery is happening, the BFT discovering is happening simultaneously. So once it uh, discovers and OSPF discovers the neighbor, it will send a request to the BFT to also initiate a BFT neighborship. And once that is done, then the BFT neighborship session with the OSPF neighbor router is established. So what happens if the OSPF neighborship is down? So when a failure occurs in a network, the BFT neighbor session with the OSPF is torn down. So they both when the failure will happen, so their BFT neighborship will turn down, and BFT notifies the OSPF process that BFT neighborship is no longer reachable. The OSPF will also turn down its relationship, and if an alternative path is available, the router will immediately start converging on it. So to configure BFD, this is just a single command that we have to note, which is okay, enable configure terminal, and this is the OSPF we are configuring on our routers, and just BFD all interfaces. That's it, and the BFD will be enabled. To verify, we could use the command show BFD neighbors and show IP OSPF. I would also tell you about the lab. So let's just, yeah, for the troubleshooting part, we could use these following commands, which is to debug BFT events and debug BFT packets. Events will display the debugging information about the BFT state transitions, and packets will give the information about the BFT control packet. And this is the same show BFT neighbors, which was which we previously saw here. For the lab thing, okay. What we'll do, we'll just, okay, I need to disconnect from the VPN. And this R1, this R2. Yeah, so let's just stop R1. Okay, we'll just, let's just search, let's just put that verification commands here and see what's the output. Show BFD neighbors detail. Okay. What's that? Oh God. So we are seeing that on BFD neighbors, we could see the details, inactive ones, MPLS also, VRFs also. So we have not configured that, so I don't think so we will get any output. So let's see. Okay, wow. So So this will show that BFT is enabled. Okay, so the neighborship has not yet been found. So it shows that BFT has been enabled in the OSPF. So that is the this is the OSPF, show IP OSPF, and yeah, all these informations are extra, and we just need to focus on that BFT is enabled. I was trying to get the log of the debug command, but I was not able to get that. I even asked Anas, but okay, that commands were not working. So maybe I could ask him later on and tell you about. That's it. And yeah, who would go next? I mean, who would go next?
Okay, I'll go next. Is my screen visible? Okay, so I have both the topic of network analyzing. So they might sound similar, but bear with me, they are a little bit different. So first I'll cover SNMP, then NetFlow, then what's the difference between both, so as we get a clearer picture. Okay, SNMP. It stands for Simple Network Management Protocol. It is a very small protocol, like it takes a very little overhead in any router, so it is lightweight, and it can be embedded in multiple local devices. You can have it in switches, routers, servers. In fact, we can even embed sensors to get the physical temperature. And then we have, okay, so why do we use it? To know the current network bandwidth, it is SNMP gives us the real-time data, the network bandwidth in real time. The CPU uses what's the temperature of various devices using sensors. We have three types of SNMP versions. Like first one was the original one which came in, and second one introduced community string. It is kind of like a password. If you don't put that password, it won't you won't be able to get or set anything. So SNMP uses community string, which is kind of a password. And the version 3 is the latest one, and which is the most improved one, because it gives us the facility of authentication and encryption so that nobody can look over your network. Okay, the components. First, we have 4 type of components. First one is the managed devices and resources. The devices itself, like which are getting managed by SNMP protocol, come in this category. Then this software runs on hardware or service being SNMP agent. This is SNMP agent is a software which runs on the devices. So basically all kind of data collection and everything is done by the SNMP agent. SNMP manager, basically what we call as NMS, network management service, kind of it is. We have all kind of data collected here. Now MIB, management information base. Management information base is the collection of all kind of object data and object identifier, that is known as OID. Okay, so this is what an OID looks like. It is like a tree. It is in a tree format. So what you can see in the brackets are represented in dots, and what we get as a final product is our complete OID. So for example, here in the case, I'll let you know like halfway, like ISO. So first integer would be 1. So in that fashion, 1.2, 0.3, 0.6, 0.1, and that way. So in that way, we will get a OID. So this is an important and interesting one. SNMP agents and NMS communication. How do they communicate? We have a plenty of communication types here. Get request, get
Is Rishita audible to everyone?
No, no, she's not audible.
Rishita, you're not audible.
yeah, I lost you people. Sorry, I'll start again. Is that okay? I mean, from where I
Yeah.
Yeah, sure.
hello.
And now you're audible.
Okay. Okay, so get request, get next request, get bulk request are the kind of like what we have seen in NetConf, right? So these are used to retrieve any kind of data. I'll show you a demo at last, so as to get a better picture. Set is used to set anything. Like if you wanna set the name of the object or something like that, we can use the set one. And SNMP response, it is sent by the agent to the SNMP manager. Okay, and this is the acknowledgement of trap and inform. Now let me tell you that basically trap and inform might look same, they are very similar, but there's only one difference, that trap is unreliable and whereas inform is reliable. Basically trap is sent once, okay, and if the NMS receives, it's well and good, and if it does not, the agent does not bother to send it again. But in case of inform, if it does not get a response, it will send it again until it gets a response. So that's the difference. And now the commands are very easy. First we need to set up the community string, which I said is the password. And now the RO or RW, as you can see here, is the read-only access or write access. Basically, if you want to give the write access or not, you can decide that. And then you have to assign IP address to the interface. That's it. And that's you're good to do. Like I'll show you in Packet Tracer. Let's go with the demo simultaneously. One second. Just share the screen. Can you see my Packet Tracer?
Yeah.
Okay. So this is the computer I will be using, and this is the router. I have not configured anything other than just I have put no shut command and IP address, and that's it. Now in desktop itself, you have a MIB browser. When you click here, you have to put the IP address of the router. Here I have put the router's IP address. In advance, you need to put the community string, the password, whatever you have configured there. Okay. And here you have some standard MIB trees. Okay. Like I'll go here. You can choose anything. We can play around to actually get an idea. I haven't done that, but suppose this. Suppose I want to get the name of the router. Okay. It is giving me the name. Now we can verify that also. It's R1, right? Now suppose I am gonna change it. Suppose I wanted to name it router. And it should be octet string because we are giving it a name, not integer value or something. Okay. We will set it. Now it is already showing router. We will check it again. Going back. See. So that's it for SNMP demo. Then let's see further. Okay. Okay, SNMP ports. First of all, we need to know that default port of SNMP is UDP 161, as you might have noticed in the packet tracer. I'm not sure if I did not pay attention to that, sorry, but it's 161. Okay, so troubleshooting SNMP. What can you do if SNMP is not working? Check for your community string. As I told, it is the password. It is, you must ensure that it is correct. Firewall configuration, then timeout. Yes, if the SNMP does not get a response within a stipulated time, it times out. Then we have to get another SNMP request. Like that. Now, understanding the error message, I won't go through it because it will be very boring. In case you ever encounter such kind of error, we can come back and see this, okay? Now, coming to NetFlow. NetFlow is again a network analyzing tool only. It's a network analyzing protocol which collects all active network IP network traffic, which is flowing in or out of the interface. Like, and why do we use NetFlow? To know the point of origin, what's the destination, the volume, path, what is the baseline of the traffic? Like on a normal day, what does the traffic look like in a system? So that is very important, so as to detect any kind of abnormality. Then what is the effect of adding a new device or service? Suppose I have added a new router or anything. Now, how does that affect my network? We get an insight about all these things using NetFlow. Again, ingredients or components of NetFlows are a monitor, exporter, and collector. Monitor, as was an agent which used to send in SNMP. Monitor is the one which will monitor the ingress or egress traffic. So basically, whatever is going in and out, it is gonna monitor it. Exporter. Now, whatever data is getting captured by the monitor will stay in the cache memory for a very short period of time. And after that, it needs to be exported somewhere because we can't really put that much of burden on a router. So that is that. And then we have the collector. Collector is something which will take up all the data, make an analysis and put it into understandable forms like graphs or reporter. And for that we have Scrutinizer. It is one of the most popular ones. So I'll show you the snippet also of that. Okay, how does the NetFlow work? IP flow, which I said, is the ingress and egress traffic through an interface. NetFlow cache also I explained. Okay, CLI and NetFlow. As I told you, there are two. The data collected stays in the cache memory for a short period of time. During that time, we can access that data in the CLI format.
Rishita, we lost the voice again.
biggest net flow limitations. Like, it's a really great technology and we can get a lot of insight using it, but problem with NetFlow is that it uses a lot of resources on our router. Like, it is quite heavy. Though we get a very detailed planned, information of what is happening in a traffic, but at the same time we are reducing its efficiency by doing so. And there are other so to what do I say, to tackle that, we have the people, what they did, they use sampling. Basically the whole traffic was not taken into consideration, just small samples of it. But still then, the data was so heavy that they had to sample so much that it gave a distorted view. So this is about that. And other than that, monitoring tools are very limited. NetFlow can't be, everyone can't analyze the NetFlow data. So this is a very limited number of tools that can analyze it, and thus it limits its uses. Okay, NetFlow commands, like how can we configure NetFlow? First of all, we need to remember that we need to configure an export. Export as in which is gonna export the data. Here we have the destination of the collector to where we are sending it. Okay. Now transport UDP, the protocol we are using, and the port number 9996 is the default port number of Scrutinizer. So we have used it here. Now in the next line, as you can see, we have used V9. Version 9 is the recent one, like it is more prevalent right now. So V9, the source from where we are sending, as I said that it is monitoring the interface. We have used an interface here as source, and that's it. We have configured that export. Now we will configure a monitor. Monitor is something which will monitor the traffic, and it is right now it is a generalized monitor. We haven't assigned it to any interface. So flow monitor, monitor's name, the capital ones are the name. Record net flow, IPv4, what kind of protocol, and input. Like we are choosing ingress traffic here. Okay. Now export, we are choosing the export for this monitor. Like we created this export, right? Export 1 here, which we will be using here. And then that's it for the monitor. Now, as we have configured the exporter and monitor, now we will go ahead and assign the monitor to one of our interface. Okay, so here we have assigned it to gigabit 0/0. That's it. And this is what I did not perform it because I was unable to. So this is something that it would look like in CLI. Like if we are giving the commands, show flow monitor name, monitor cache. So basically in cache memory, we have this data already here. And this is the snippet of the Scrutinizer. As you can see, it is giving us a lot of data in various forms, like what kind of domain application did they use, HTTP, HTTPS, or anything. We are getting that. What was the location and everything. So we can, perform a detailed analysis of the traffic. Okay, so coming to the real point, FNF, flexible net flow. So basically this was made to tackle the limitations of net flow. Now what we have here is what I said, that the overhead traffic, the overhead load on the router was a lot. So we tried to tackle that by limiting, like we are here manually telling everything. Like what do we need? So basically it's more customization so that you can just choose whatever you need and you can just collect those information and perform analysis on it. So anything useless won't take up your space. So that's it. I have installed I have given a configuration guide here because the configuration was quite long and we just went through the simple configuration of NetFlow. So I'll just skip that. Okay, troubleshooting NetFlow. Again, this is something if you're getting any kind of error or you want to debug something, NetFlow troubleshooting, this is where we will get all kind of commands. This, I won't be discussing this. And coming to the real deal now, SNMP and NetFlow, what was the difference and which was better? So as I told you, SNMP and NetFlow, SNMP gives us the real-time data. We are doing it in the CLI itself. It is giving us the real-time data and thus we can analyze. But in case of NetFlow, it is getting collected then the exporter sends it. So there's a little bit of time gap, which will never be in, no matter how fast it is, it will be a little bit lagging behind. Okay. So though it will again provide, always it will provide the beginning and end time of the flow, like when it was captured. So you can get an idea, but it won't be in real time. Okay. SNMP does not give the details. As I may say that it is just the overview. It is real time, it is just the overview. It will give the answers in graph, but that's just the overview. How much bandwidth is it is using and all, but it won't give like which application is using how much of bandwidth. So that is done by NetFlow. Consume less disk space as it is real time again, and NetFlow is heavy. Then SNMP can be used to collect CPU and memory utilization. NetFlow can't do that. SNMP has a wider vendor adaptation, real-time characteristics, and low resource consumption. Then fault management and quick network performance overview. That I said that it won't give the complete details, but you will get the gist of everything. And NetFlow is very accurate. Obviously, it will give very accurate, detailed information of the network traffic parameters. So I hope that was clear. Like a little bit of difference and how they are different, but they are doing nearly the same thing. Like their main aim is the same. Okay, that would be the end. I'll just paste all the links I have used here in the slide before sharing. And that's it from my side. Thank you. Thanks, Ashan. Dhanush. Okay, Dhanush. Thanks, Parul.
Oh, yeah, guys, I have Anna's message now. We have meeting at 5:15, so I have another meeting till 5:30. So I messaged him. So he said no problem. Also, he asked that wait a second, I'll just open his chat. He said that have we started with the presentation? I said yes, we are presenting to each other and almost done with that. So he said good, we'll just take a look at 5:30. So
Okay.
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 It
Yeah,
just
sure.
just
Okay.
yeah, just a look.
okay. Yeah. I won't take up much time. I'll just yeah. Is my screen visible?
Yeah.
Yes.
Yeah. Software upgrade and redundancy failures. So we had gone through software upgrade yesterday, and we know how to upgrade our software right now. So what all do we need to keep in mind when we are upgrading our software? So when I went through the documentation, there are three exact points that the documentation stresses on. First one is the ROM ROM monitor, which is I'm not quite sure clear on it, but it's an integral part. I think it goes along with the upgrade. Cisco recommends that the ROM1 version has to be greater than 15.6 or higher. And also, if you're doing in-service software upgrade, the minimum version must be 15.6 or higher. So in order to check which ROM1 is actually going on, you can use the show platform command. When you use the show platform command right here, this firmware version that you get over here, this is the ROM monitor version. In case this is less than the required version, then you need to upgrade ROM1. In order to upgrade ROM1, this is the step. You need to download ROM1 software from the cisco.com cisco.com website itself. And then first you have to check which slot your ROM1 is active in. So this information is available right during the boot of the Cisco router. So right when you get the boot, you get all these messages, and you get here a boot from ROM0. So ROM0 means that your RSP from slot 0 is active. So you need to upgrade ROM1 from that version first. It is recommended that you upgrade both ROM1 versions. So this is how you find out which ROM1 is active right now. First, you'll get the package from cisco.com, and then you have to copy it to the boot flash, and then first copy it to the boot flash, and then run this command, upgrade ROM monitor with the file name, with the boot file name in the boot flash, along with which slot you want to upgrade, R0. And then again, you can run the same command for R1. Before that, you have to reload the router. Each time you do it for a single slot, you have to reload the router. So the first main thing that you have to keep in mind is ROM1 version. So other requirements is memory. In case of 902, 920s, there was a memory specification that must be needed, which was 2 GB DRAM. It was all in the data sheets. And then also the validity of the package itself, or else we'll get an error in the RSA or SHA that we saw yesterday. And also the downloaded image must be in the same directory as the base image. The base image that is running in the Cisco router right now, the downloaded image, the new image that we have, it must be in the same base image. And also there's something called a package.conf file. In case it's an auto update, whatever ISO file, whatever image is there in the package.conf file, that will be used. So you shouldn't move this to the directory that is directory of the base image. It must be there within the different sub packages in boot flash itself. And also the boot command, if it's not executed properly, there will be a set of errors. It will just revert back saying that the boot is failed, and it will restart. Okay, so there are two steps. One thing you can just the normal upgrade that we did yesterday, and then the second one is ISSU, that is in-service software upgrade. For 900 series, for 900 series, there are two types of packages that we know. One is consolidated package that we run with a single package name, and then various other packages. This is in order to upgrade using the sub package mode. The same configuration that we run in the lab yesterday. First, we have to. This is in order to. Config register in order to set the register for booting, so that the right file is booted. And then this request platform software package that we run yesterday, that's actually mainly in case you have a redundant RSP and you need to include the boot flash image file within that standby RSP as well. In case if you are running it in a single RSP, this command is actually not needed. That's what the documentation is saying. And then finally, this is our main statement, boot system with the boot flash, the image name that we have. And then this command actually copy running. This is just saving the config in case if you don't run this also, the router will prompt us in if you want to save the present config or not, and then reloading the router. We had seen the live demo of this command yesterday itself. The second type of software upgrade is ISSU. In order to run ISSU, there are a few checks that we need to make before ISSU is actually ISSU can actually be executed. The first one is check the device documentation, and we have to refer the ISSU support matrix to check if this is your base version, the version that you are running right now. This is the version you want to upgrade or downgrade. If this version is NS is supported, then only you can use ISSU in that the upgrade or downgrade process. If it is not supported, then ISSU is not possible. Along with that, you also have to check for redundancy using the show redundancy. If there is no redundant RSP, you cannot run an ISSU upgrade. And also the ROM1 version. As I said from our first slide, there's a particular, for each product, there's a particular ROM1 version which is compatible for ISSU. I think it's 15.2, if I remember, 15.6, yeah, 15.620. If it is less than that, then ISSU is not possible. So ISSU also can be done in two ways, using a single command and then using multiple steps. Before conducting ISSU, we have to go to what is called we have to first download the file from the Cisco.com onto our chassis, and then open an console session to the RSP. And also make sure that the image is in the same drive as the base image. It has to be in the same, and it has to be in the active RSP. Yeah, there's no need to copy your image into the redundant RSP. That is done by the auto update itself. You have to just copy it into the active directory of the active RSP. Before you run the single command, you have to set up the router as well in order to go to what is called a SSO mode. SSO means, I'm sorry, I keep forgetting that acronym. Stateful switchover. Yeah, the main part of ISSU, that is in order to switch over without losing one state. Yeah, I'm sorry. Yeah, these commands that bring the router into a sub package mode, boot it from a sub package mode, up to our configuration number 7. This has to be done for ISSU as well. ISSU as well. You'll expand the package that you have, the image package that you have, into the standby router as well. Sorry, standby RSP, and then you'll configure the boot system with the package.conf file. After this 7 statements, we'll have to move the terminal to an SSO mode, that is a switch to state over mode. Configure the terminal, then redundancy, it will move to a redundancy configuration mode. Move the terminal to SSO mode. Once you wait for some time, you'll get an terminal output saying that terminal has reached for SSO mode. After this, you can execute a single command which will run the entire upgrade for you without losing connectivity, that is internet connectivity. So request platform software package, install, node file, and the file name that you have. This interface module delay, what happens is we have many IMs, that is interface modules. In order to keep them running, there will always be some kind of delay when there's a large scale of upgrade going on. There are 20,000 to 30,000 modules. When such upgrades are going on, there will be a delay. In order to adjust to that, we give interface module delay as well. Okay, this is it for upgrading. So main things that we have to keep in mind is memory, ROM1 versions, and then if ISSU is being executed, all the terms that are met. Is the ROM1 version correct? Is there redundancy? And then is ISSU really applicable? The next part of my presentation is about redundancy. So redundancy is when you have 2 RSPs, routing switching processors, in your ASR 9000 device. To check if your device has redundancy, use the show redundancy command. It will give you a set of this output, and you'll know if it is configured for being redundant or not. There's also one more command, show platform. By show platform, you'll actually, when you have show platform, you'll actually have 2 more inputs here for another RSP, which will be in standby. Before that, you can use show redundancy itself in order to check if you have in standby RSP. I could only find two troubleshooting, 2 failure problems for redundancy. The first one was, what if your routing processor is in status unknown? When you give show platform, what if your routing processor slot is giving unknown? That is, it's not able to identify. This happens because RSP will keep toggling between booting and unknown, and it will not go to your standby state. It is mostly because of missing our XE image, which is missing in the local boot flash. In order to work around this, we have to use an USB flash drive with a valid XE image and then boot the RSP. If still the unknown state keeps on recurring, then we have to physically reset the module. Resetting is you have to again insert it back. The second use case that I could find was, what if your standby RSP keeps on toggling between booting and init standby instead of booting and unknown? It keeps toggling between these two. The common reason for this happening was there was a configuration sync failure between active and standby RSP. This is the most common, but this is not exactly, this could be the problem, but this is the most common. Around 90% of the case, this is the case that there's a configuration sync failure. So in that case, you have to verify using these three commands: show redundancy, config sync, failures BEM, MCL, and PRC. In any case, if there is an failure output, then you have to then this is the problem that is causing the toggle between booting and init standby. In that case, there's a workaround given. You have to go to the SSO terminal mode and you have to execute two statements: policy config sync, LBL, PRC reload. Again, you're just reloading LBL and PRC. Once you reload this, your standby RSP will go into init standby. So these are the two. These are the only two use cases I could find for redundancy failures, and on upgrade failures as well. That's it for my presentation. If there's any questions?
No. That's
No,
all
no, no.
good.
Thank you, thanks, guys. Thank you, man. Thank you, Arjun. Thank you.
Yeah. Okay then.
Arjun, you
So
could
can I
pause the recording.
stop. Yeah.